The James Webb Space Telescope is now in the middle of a 3-month effort to unite its 18 mirror segments into a single mirror. What started as 18 random smudges of light have now transformed into what appears to be a single image of a star. And if that weren't cool enough, we even got to see an actual selfie image of Webb's primary mirrors illuminated by starlight for the very first time. It's been a while since we last chatted about Webb, but a lot's been going on behind the scenes, and I thought it'd be fun to catch up on what's been happening. Much of it involves the alignment of Webb's primary mirror segments. And we took a look at the overall optical system in a previous video. But now that the alignment is in process, let us take a closer look as to how it started, how it's going, and what's next. The process began in February when Webb was pointed at the star HD 84406. It's an otherwise nondescript star in the constellation Ursa Major, but it was chosen because it's relatively bright and also fairly isolated in the sky. Now by bright, I mean that it has an apparent magnitude of 6.9, and that's still too faint to be seen with the unaided eye. But that's very bright for Webb to find, especially with its mirrors out of alignment. Segmented telescopes like Keck use a dedicated instrument called a wavefront sensor that's specifically designed for alignment and calibration of the mirror segments. But internal space on board Webb is at a premium, so the near-infrared camera, or NIRCam, was designed to double as Webb's wavefront sensor. The camera's wide field of view helps to find the star quickly, and it was equipped with specialized components just for the alignment process. The expectation was that there should be 18 separate images of the star because there are 18 individual segments. The imaging began on February 2nd and lasted about 25 hours. During that time, NIRCam snapped 1,560 images over 156 individual pointings. As it turned out, all 18 images were found pretty much right away. The team also performed a focus sweep of the secondary mirror. And this is much like when you are initially focusing in a backyard telescope. You'll turn the focusing knob all the way in one direction and then all the way in the other to find out where the best focus is. After the sweep, the team set the secondary's focus for the initial alignment. Another thing the optical team needed to do was to assess the alignment of the telescope to the instruments. So NIRCam took a selfie of Webb's primary mirrors. NIRCam is equipped with a special lens called a pupil imaging lens. This lens has just the right focal length to short the star's image before it reaches the detector, and then relays the previous pupil onto the sensor. The result is an image of the pupil instead of an image of the star. What's really cool about this image is that you can see that one of the segments is lit up because that was the mirror that was aimed at the star when this image was taken. Of course, there's a fair amount of noise in the image as well, and that's because the telescope still hadn't cooled down to its final operating temperature by this point. So the mirrors, the struts, and even NIRCam itself were still glowing thermal noise into the image. The good news is that as NIRCam cools down, the thermal noise will largely disappear and the image quality will dramatically improve. The next step was to determine which of the 18 smudgy star images belonged to which mirror segment. And this was done by using actuators behind each segment to make tiny tilts, one segment at a time. As each mirror was tilted, its corresponding image shifted as well. So this approach allowed each of the 18 images to be tagged to its mirror segment. Next, the segments were further adjusted to bring each image into a hexagonal image array. And this was done to give the Wavefront team an intuitive way of visualizing the segments as they were nudged into alignment. But many of those images were still out of focus. And part of the reason is because each movement of the segments introduces a tiny jitter into the telescope. So the fine guidance sensor was brought online to lock onto a guide star and guide Webb for the first time. FGS takes 16 measurements of the guide star's position every second and sends adjustments to the fine steering mirror. The fine steering mirror is Webb's image stabilizer, which freezes the target into place. So with the FGS up and running, the segment alignment could begin. Now, the idea here is to correct most of the large positioning errors of the mirror segments. First, the segment images were slightly defocused by moving the secondary mirror by a tiny amount. A mathematical analysis called phase retrieval was then applied to the defocused images to figure out the precise corrections each segment would need. The segments were adjusted by the prescribed amounts, the secondary was returned to its original focus, and the result were 18 more or less focused images. The next step would be to bring those images together for the first time. Webb's 18 segments are divided into 3 groups of 6 segments each. Starting in mid-February, the groups were sequentially commanded to stack their images. And this is an iterative process where the segments are tilted, an image is taken, then analyzed, then new tilt commands are uploaded, and the process repeats. But by the end of February, all 18 images were stacked together for the first time. But you might be wondering what's going on with the rippled spikes surrounding the star. Well, it turns out that these are due to the effects of diffraction. You see, light waves have a tendency of bending around the edges of an obstacle or an opening. And when this happens, the waves interfere with each other and alternate between canceling and amplifying each other. You can really see this effect when you shine a laser through a pinhole. As the light waves pass through the hole, they form these diffraction rings around the center. But light also diffracts around obstacles, in this case, the 3 support struts of Webb's secondary mirror. The result are the 6 characteristic diffraction spikes. Now, Webb's secondary struts were designed to minimize this effect as much as possible, but struts are always going to produce spikes because physics. Still, it's pretty though. However, it's really 18 diffracted images of a star stacked on top of another. And that's because the mirror segments are still acting independently of each other. In order for the segments to act as a single mirror, they must be aligned to within the wavelength of light. Now, this is a process called phasing, and it's done in 2 major steps of coarse and fine phasing. Throughout the alignment process, these phasing steps are going to be repeated in 3 rounds. So as of this filming, the optical team are still in their first round of coarse phasing. Now, to understand how this works, let's consider 2 segments next to each other, with one extended a little further out from the other. This difference is called the piston error. The piston error can be measured using a clever technique called dispersed fringe sensing. Here's how it works. Starlight from the 2 segments is dispersed into what is essentially a spectrum. If the piston error between the segments is large, the spectrum takes on a barber pole pattern. By analyzing the fringes in this pattern, the piston errors can be determined very accurately. As the segments are corrected, the barber pole flattens into a thin braid. Because there are 18 segments to align, NIRCam uses a pair of masks called dispersed Hartman sensors. This is an array of slits that line up over 2 segments worth of the image. NIRCam carries 2 of these masks, each offset by 60 degrees so different segment pairs can be measured. The piston errors are then used to make adjustments to the settings. After the first round of coarse phasing, the segments should close to within about 5 microns of each other. Now, that's 5 millionths of a meter. But in order to achieve the expected performance, the mirrors will have to be aligned to within a few nanometers or billionths of a meter. Now, any large imperfections in the field are likely due to the secondary mirror being just a little bit out of alignment. So some corrections to the secondary's positions are made, and the fine phasing begins. Now, during fine phasing, the images are defocused once again to measure and correct the remaining alignment errors like we saw during the segment alignment. However, in that earlier phase, the images were defocused by adjusting the secondary mirror. But during the fine phasing, the secondary needs to be left alone because now it's pretty much back in focus. So NIRCam uses weak lenses in its pupil and filter wheels to defocus the starlight by specific amounts. The phase retrieval algorithm then analyzes the defocused images and works out exactly what phasing errors remain. The segments are corrected, but this time by making tiny tip and tilt adjustments instead of piston adjustments. After corrections are made to the segments, a second round of coarse phasing is done to further isolate and reduce any remaining piston errors. And that's followed by a second round of fine phasing, and then that's followed by a third round of coarse and fine phasing. By the end of the 3 rounds of phasing, the mirrors are very well aligned, at least as far as one of NIRCam's fields is concerned. But NIRCam can only see the center of Webb's science field of view. The rest of the instruments are looking elsewhere in the field, and any tiny errors remaining in the mirror's alignment will need to be corrected. First, Webb takes 5 defocused measurements of the same star in each of the instrument's fields. Now this time, the images are being defocused by moving the secondary mirror out of focus by about 100 microns. The phase retrieval algorithm determines the remaining tiny adjustments that are needed on the segments and to the secondary to fully correct the entire field. By the end of this process, the mirrors are now being adjusted by just a few nanometers at a time. In other words, just 1/10,000th the width of a human hair. It's a painstaking process, but it's also a flexible one. Previous steps in the process can be repeated whenever needed, and like everything else, there are contingency plans for when things go wrong. But right now, the team are about halfway through their 3-month alignment process. When that's done, they'll continue with the commissioning of the instruments as they cool to their operating temperatures. And then, science. But even after Webb is fully commissioned, the telescope will likely drift out of alignment from time to time. And that's because the telescope structure will continue to slowly outgas for years to come. And that will introduce tiny changes into the alignment of the mirrors. And that's why fine phasing measurements will be taken every 2 days and analyzed to track the telescope's alignment over time. A small correction will likely be applied every couple of weeks or so. Now, one thing that's pretty clear about this approach to maintenance is that it really underscores the idea that once you have everything set up, it's much easier to make frequent yet tiny adjustments to keep it running than to wait until everything gets really bad. I know that's easier said than done, but the good news is that's a skill that you can master. And that's why I'm so grateful to have Skillshare support for today's video. Skillshare is an online learning community with thousands of online classes and members across 150 countries who come together to find inspiration and to level up their creative game. And this year I'm making a point of finding ways of creating content more efficiently while bringing as much value as possible. That's why I'm enjoying Productivity for Creatives by Thomas Frank, where I'm learning how to build out a system that lets me improve my channel without getting bogged down in so many details. New premium classes are launched each week and are presented ad-free, so there's always something new to discover while staying in the learning zone. Now, if you want to level up your game, the first 1,000 people to use this special link will get a 1-month trial of Skillshare absolutely free. Make sure you use the link in the description of this video. And speaking of supporting Launchpad, my gratitude as always to my Patreon supporters who are helping to keep this channel going. And I'd like to welcome Benjamin M. Day, Scott Horwitz, Dandeep Jain, Stephen Youngier, Matthew Jackson, Michael Cobb, Phil Light, Leela Nagalingam, Nils M., Richard Pakras, Riva, Jeff Rodman, Joe Rodricks, David Turner, and Holly Vernon. Thank you so much for supporting Launchpad Astronomy. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.